Okay, can you hear me now? Fine. All right. I think we can get started now. Okay. This was such a waste of time. Right. So I was asking you whether you have solved this, right? Are there any problems with these four questions? That's what I was asking you. Do you have any problems with these four? It's too low. Okay. Yeah, I understand. I know that's a problem with this earphone, right? I'll try to shout as much as I can. All right. Whenever you don't hear me, but please just tell me, right? Can you hear me now? Okay. Maybe I'll just have to keep it like this. Time to get a new earphone now. Okay, fine. So I was just asking you whether you have had any problems with these four questions, right? And looks like no. Okay. All right then. Let's go over to the next. Go to, we're going to exercise. No, yeah, before that, actually, there's something that was pending since last 2 days. I must tell you that. Raj asked us, you know, Raj had a question, what is specific resistance? All right. And I read the whole book and I didn't find it anywhere. So specific resistance is not given in your book. All right. Not given in your textbook. All right. Okay. So then we will follow what I've read in physics books, right? Most physics books say that specific resistance is resistance per unit length. So this is what we'll follow. But like I said, this is not given in your textbook. So of course, this will not be asked in board exam. There is no doubt about that. All right. Okay, so you could call it resistance per unit length. Okay, this is resistance per unit length, right? And there's one more thing that I want all of you to write along with the microscopic form of Ohm's law. Okay, right? Wherever you have noted down microscopic form of Ohm's law, just one or two lines, okay? Not big, don't worry. It will only take a little bit of space, right? Okay. It is that if you remember, we derived that E is equal to rho into J, correct? Okay. And there we stopped, right? So we stopped over there because at that time I did not tell you about conductance. So now, of course, I have told you about conductance, and we can use that sigma is 1 upon rho. And if you use that, you can get J is equal to sigma E, right? I mean, this is not that tough, right? It's quite simple, but I thought let me just mention it so that it doesn't go out of sight, right? Okay. I hope that is absolutely clear to all of you, right? Okay, so make sure you write this where you have written the microscopic form of Ohm's law. Okay, maybe as the last slide. All right, just one simple step, right? And this is its reason. Okay, and if you want to write it in vector form, of course, like this, right? I don't think anyone has any problem with that. Okay, fine. So that's all I wanted to mention, right? Now I think we are going to solve exercise question 13. Right, let me just confirm that with the list I have made for each topic. Okay, just give me a moment. You can start reading that question. Yes, exercise question number 13 is what we are going to do now. All right, 1 3. Okay, I'll just copy that question now from the book. Okay, all right. So, okay. Right. So, number density of free electrons in a copper conductor so is given. Number density of the electrons is 8.5 into 10 raised to 28 per meter cube. Right. The question is how long does an electron take to drift from one end to one end of a 3 meter long wire to its other end. So what we are given is that suppose this is a straight long wire. Okay, suppose this is a straight long wire and it is 3 meters long. Then how much time does one electron take if it is supposed to drift? Okay, again we are ignoring random motion, right? We just have to consider that suppose an electron would only be drifting. All right, suppose an electron would only be drifting, then how much time would it take for this electron to go from here to there, to drift from here to there, right? Okay, area of cross section is given and current is given. So of course I hope you realize we want to find time, so time is going to be 3 by vd, right? I don't think anyone has any problem with that, right? Okay, because length is 3 meter. Okay, so now use we are going to use the formula for vd that it is given in the question, right? Vishwa, it is given in the question how much time would it take for an electron to drift, not move, right? Okay, so I is equal to n e a v d, right? Okay, so if we use that we can just put vd's value, right? So what is going to be vd's value? We have, I really hate this wire. We have 3 divided by, instead of vd you can write I upon NEA, right? Okay, and I'm sure you understand that rest is simple calculation. Okay, no surprises here, it's very, very simple. That's it. Current is 3, right? That's it. Clear? Okay, find the answer, come on. What's the answer? What's the answer, everyone? Okay, right? Hmm. So most of you have got this 2.72 into 10 raised to 4 second, right? 2.72 into 10 raised to 4 second, right? So that's a long time, isn't it? If oh sorry. If you think about it, this is actually 27200 second, right? So it's what, about 6 to 7 hours, right? That's about 6 to 7 hours, right? Okay, in fact more than, yeah, 7.5. Okay, sorry, more than 7 hours, right? I didn't divide it exactly, I just gave it a rough shot. So more than 7 hours, right? So this is actually an I mean, it's obviously because that drift velocity is very low. I hope you remember the answer of what we solved earlier, right? So that is because drift velocity is very, very low. Okay, right? Now, let's proceed. Okay, now we are going over to the next topic, right? And that is going to be mobility. All right, that is going to be mobility. It's a very, very, very small thing, very simple thing. All right, okay. So we go to mobility. See, mobility refers to, or mobility in English means how easily such something moves. That's called mobility, right? How easily something moves. That is called mobility. But here we are going to talk about mobility of electrons. Okay, here we are going to talk about mobility of electrons, right? So this is about how easily anything can move or any electron could move, right? So it has a proper definition here. So here's the definition. Mobility is the ratio, mobility of charge carriers. Do you remember charge carriers from semiconductors, everyone? And do you understand it as well? Do you remember what are charge carriers and do you understand what are charge carriers? Okay, charge carriers are particles that are responsible for transfer or movement of charge, right? For example, in metals, when free electrons or conduction electrons go from one place to another place, we say that charge is flowing, right? Similarly, if you will think about semiconductors, then in semiconductors electrons move, right? And there's something called holes, right? So those holes also move, right? So there are two types of charge carriers over there. In metals there is only one kind of charge carrier, and that is electron, right? Now this definition is actually true for either way, right? It's not necessarily only restricted to electrons. You can use it for any kind of charge carriers, all right? So the definition is it's the ratio of the drift velocity and the electric field applied, right, which is causing that drift. I hope you remember that whenever electric field is applied, it causes some drift of the electrons, right, or of charge carriers. So here this would mean we already know that Vd is equal to E tau by M, correct? I hope all of you remember that. Agreed, right? So based on this, mobility, just simple thing, mobility mu, symbol of mobility is mu, right? Symbol of mobility is mu. So mu is equal to Vd upon E. So easy, right? So it's going to be E tau by M, right? It's going to be E tau by M, right? If there is some other charge carrier, suppose it's not electron, right? If there is some other charge carrier, then mu is equal to Q tau by M, right? So where M is going to be the mass of that charge carrier and Q is the charge, magnitude of the charge, all right? So for semiconductors, actually you can write it in this way. For semiconductors, you could write mu is equal to mu of E and mu of holes together, right, added, because both will have their own mobility, right? So then this would become E tau by M, right? And this is something very weird, right? And here also you have to write E tau by M, right? Okay, right? So typically in semiconductors, when they are intrinsic, mu E is equal to mu H, right? Okay, at normal or room temperatures, this is what uh, normally happens. All right, this is what happens. Anyways, right? So, like I said, when there are multiple charge carriers, then you would have to take both mobilities, right? But again, this chapter is mostly about metals, like I said earlier. So here we are not going to worry about holes. We'll only worry about the free electrons. All right. Okay. So that's mobility. Again, mobility means how easily the charge carrier moves. You can you can see that over here. This mobility depends on charge, relaxation time, and mass. That's actually reasonable. I hope all of you understand why it's like this. Because if it is heavy, if the charge carrier is heavy, it will not move easily. Agreed? Right? Similarly, if relaxation time is very less, if relaxation time is very less, then that would mean that it's not getting time to move, right? Because suppose one ion is here, another ion is here, let's say, and the electron simply is to go from here to there, right? But if the spacing, if the distance between the two ions is very less, or if there are lots of collisions going on, if there are more collisions going on, and if tau is less, then it will not get time to accelerate, will not get time to accelerate, right? I hope that makes sense, right? So obviously drift velocity will be less and mobility will also be less. That's what I'm talking about, right? So if t is less, mu is less. So that's because of this, right? And this E plays a role as in if charge is more, it will experience more force. I hope you get that. If Q is more, then that charge carrier will experience more force, right? Okay. If Q is more, there is more force. And if there is more force, that would mean the mobility is more, because of that higher force, the charge carrier will try to move fast. Okay. Right? The drift will be more actually, right? So we are talking about the drift here, right? So the drift will be more. So these are the three factors on which the mobility typically depends, right? Now, if you take this formula, right, this is it about mobility, but there's something extra I want all of you to know, right? If you look at the rho formula, sorry, if you look at the sigma formula, right, sigma is equal to n e square tau by m, correct? Right? That's what we have derived earlier, right? So if you look at it, we have the same thing here. So if I put it over there, understood? Right? So we get a relation that sigma is equal to ne mu, right? Sigma is equal to ne mu. Okay. So what this is telling you is that there is a very simple relation between conductivity, don't forget sigma is conductivity, and mobility, right? And there's one more factor, and that is number density, right? So, so now I hope you realize that if free electrons are more in number, if free electrons are more in number, then obviously sigma will also be more, right? And similarly, if mobility is more, then also sigma is more, right? Okay, that is conductivity is more. So, right? Okay. So based on this, everyone, based on this, we are now going to talk about limitations of Ohm's law. Okay. Sorry. Oh no. Before that, sorry. Just a minute. Not we are not going to talk about limitations of Ohm's law. We are first going to talk about uh, the change of resistivity with temperature. Okay. We are going to talk about variation or change of resistivity or conductivity, as you want to call it, with temperature, right? Okay, that is, as temperature changes, how does resistivity change? Okay, right? So now this part does need a lot of information related to chemistry, right? So if you have paid a lot of attention and if you have understood all the chemistry that has been taught to you so far, you will not have a lot of problem with this. It's fairly simple. So let's start. So first of all, we are going to talk about insulators, right? We are going to talk about what happens in insulators, right? Okay, or semiconductors. Actually, both have same, so I'll just explain everything together, right? Both have more or less the same logic or same reason. So let's cover both of these together. All right. Okay. See, over here, I'm just going to write the sigma formula, which is Ne squared tau by m, or you could just write the rho formula. Okay, either one will do to understand what's going on, right? And I hope nobody has any question that this would happen, right? Okay. If you don't understand this, please, you need to do a lot. Okay. So let's start. So what happens in insulators? Well, let me tell you what happens first of all, right? Okay. So this is the graph, and then we'll explain why it happens. This is the graph of resistivity with temperature, absolute temperature, okay, in Kelvin. This is the graph of resistivity with temperature. All right. Okay. So this graph takes a form like this. Okay. Exponentially decreasing kind of graph. All right. Exponentially decreasing kind of graph. Right. Okay. So basically, I can just explain all this in just one sentence. As temperature rises, resistivity decreases. All right. Okay. T goes up, rho goes down. Clear? That is what happens. Now, why does this happen? Let's talk about that. Okay. So this is what happens, and now why. Okay. So if you look at the rho formula, I know, listen to this. I know that we derived it based on Ohm's law, and Ohm's law is not valid for semiconductors or insulators, right? That's the first thing. But the general principles still apply. So that is, I'm saying that rho depends on few things, right? Rho depends on few things. M is mass of the charge carrier, right? Or whatever is making the, whatever is carrying charge with it and flowing, right? Okay. So mass of electrons, of course, does not change. So this is constant, right? E, charge of electron, constant. So now there are only two things that can change, N and tau, right? So what happens in semiconductors and insulators is that as temperature rises, okay, electrons or more electrons get free from their atoms. All right. So what I mean to say is that at low temperature, at low temperature, Okay, so you could also write this as at low temperature, N is low, right? That is the number of free electrons is actually very less. In fact, I'm sure you, if you remember this from semiconductors, you would immediately realize this, that this is exactly what happens in semiconductors, right? At low temperatures in semiconductors, there are very few free electrons or conduction electrons and very few holes. But as temperature will rise, the number of free electrons and number of holes will increase, right? Is this okay? Right? At low temperature, N is low, but as T will increase, N will increase, right? I hope that made complete sense to you. So what about the other factor? There is other factor also, tau. Tau stands for relaxation time, right? So there is a competing thing, right? There is a competing thing, right? It is that as T will increase, tau will decrease, because tau stands for sorry, what does this tau stand for? It stands for the time between two collisions, correct? This stands for time between two collisions, correct? So if temperature will increase, obviously random motion will increase, right, of anything. So if random motion will increase, the time between two collisions will actually decrease, right? Okay, but tau will decrease, all right? Tau will decrease. So resistivity should increase, but it doesn't happen. Reason is that this factor is not that great or not that large. This factor is not that large, all right? So to sum it up, in semiconductors or insulators, temperature will increase, N will increase a lot. Okay, tau will decrease a little bit. All right, tau will decrease a little bit. So overall resistivity will decrease. All right. Okay, I hope you understood this whole thing. So which is more dominant or which is more important effect? This is the more important effect. All right, and this is negligible effect. Clear? So this is what happens in semiconductors and insulators, right? So do not forget this, right? And here I've summed up the reason. એટલે આ વસ્તુ તમને થિયરીમાં પૂછી શકે, right? Explain the variation of resistivity for semiconductors with temperature. Clear? So you have to say what happens and you have to say why it happens. Clear? Whether you believe it or not, this direct question has been asked at least thrice in JW, right? At least thrice in JW. I'm shouting, Purvendra, there's not much I can do now. Okay, still, let me try again. All right, I hope it's slightly better now. Yeah, you can definitely wear earphone. That would make it very easy, right? Okay, fine, no problem. So that's it for insulators or semiconductors. All right. Now let's go to metals. Okay. B. What happens with metals? Now it's too loud. Then you can always decrease the volume on your side. Okay. So let's talk about what happens in metals. So first of all, in metals, the variation is opposite, right? In metals, the variation is exactly opposite. It's more like this, right? Here the variation is exact opposite, right? In fact, okay, and generally, it's not like very sharply rising or so, right? But it's curved, of course, not a straight line. Okay, but yes, for small variations, for small change or for small variation in temperature, okay, we can also draw this kind of graph. Okay, so what I mean to say is that if you consider a small change in temperature, then we can say that resistivity varies linearly. Okay, for a small change in temperature, resistivity for metals varies linearly. Okay, but yes, overall for a large change, this is the correct graph, and this is only approximate, let me tell you that. And you can only use this for small variation or small change in temperature. All right, any confusion? Are both these things clear? I want to know. For small change, you can say that this is approximately linear, but correct graph is this one. Okay, now we are going to talk about why should it be like that. Okay, why should that graph be like that? That is, why should the resistivity increase with increase in temperature? Okay, right? So that's what we are going to discuss now. So this is what happens. Okay, first of all, let me just write it in words what happens. Right? It is that as temperature increases, resistivity increases. All right? Okay, and again, for small change, it is increasing linearly. All right? Okay, for small change, it is linearly increasing or increasing linearly, but for big changes, actually, it's not linear. That is, this graph is not actually a straight line. All right? So please keep that in mind. Oh, yeah. Okay. So why does this happen? Once again, we are going to talk about the formula of rho. Rho is equal to, once again, what is that? M upon Ne square tau. All right. So this is rho. So now here, let's focus on these two factors once again. See, we are talking about metals. Don't forget, we are talking about metals. And metals are so nice. They have already made almost all the electrons which can be free. The electrons are already free, right? I hope you understand that metals don't like to hold on to their electrons a lot. Okay, so by taking little bit of energy, they will make them free. Agreed? Right? So, what I'm saying is, as temperature increases, as temperature increases, N remains almost constant. N remains almost constant, right? I mean, truly speaking, it would increase, but very little. Okay, truly speaking, N would increase, but very little. Okay, but like I've said, because free electrons of metals are generally free, right, at almost all temperatures, it doesn't matter, right? Even if you heat it and give it energy, the free electrons have already been free, right? Now they can't be more free, right? Okay, so the number of free electrons per volume or number density will not change. It will remain almost constant. Truly speaking, it increases very little. right? This is so less that you can almost ignore it, right? In fact, you're going to find that most books say that it does not increase, right? That's not correct. In every material, if you give it more temperature or more energy, there will be some more free electrons. There is no doubt about that, right? But that increase is very negligible. But as t will increase, of course random motion will increase, right? So if random motion will increase, tau will decrease, right? Agreed? If random motion will increase, tau will decrease, right? So here what happens is that as t will increase, n will remain nearly constant, fine. Okay, but tau will decrease a lot, and because tau will decrease a lot, that means the end result is that rho will increase. Clear? So here the important or the dominant factor is this. Clear? I hope that makes total sense to everyone, right? Okay, so in which materials will resistivity increase with temperature increase? Come on. In which material with will resistivity increase with temperature? બે જણને જ સંભળાય? હા, સંભળાણું સંભળાણું. Very good. Metals. Yes. And in semiconductors and insulators, it will decrease with temperature, right? That is, if temperature will increase, resistivity of semiconductor or insulator will decrease, right? Okay, so please keep this in mind. Also try to remember the graphs if you can. Okay, they're not very tough to remember, right? Okay, and finally, just one line before we finally finish this topic. It is that I said that for small changes in temperature, okay, let me just write it on a new page, all right? Just over here. So for small changes in temp, oh, 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 sorry, the page got changed. Yeah. For small changes in temperature for metals only, all right? This is only for metals. Don't use it for anything else. For small changes in temperature, you can use formulas that are like the change in length or change in volume with temperature. I hope you remember in 10th, sorry, in 11th standard, not 10th, you studied this. L equal to L0 1 plus alpha delta T. Do you remember this? Everyone? Okay, fine. Do you remember this? All right. We used to we. We used to study this in 11th, right? In thermal expansion, right? So just like that, okay, just like that, this is what we have here. Okay, same formula. And of course, along with that, you can also write it like this. Okay, and along with that, you can also write it like this. આ ત્રણ ફોર્મમાં લખતા હતા આપણે, બરાબર ને? All the three are the same. I hope you realize what I'm saying, right? All the three are actually the same thing, right? Okay. તો 11th ની ફોર્મ્યુલા યાદ હોય તો કઈ નવું કરવાનું નથી. And okay, so that's it. Clear? See, based on that, I don't think if you consider that for small change in temperature, if L and A are considered constant, for small change in temperature, if L and A are considered constant, then you can write similar relations for resistance also. Agreed? right? I hope you don't have any problem with that. Okay. Oh, clear? So these are similar relations for resistance. બે એક જ છે અને 11th માં આવ્યું તો ઈ જ છે, કઈ નવું યાદ નહીં રાખવું પડે. Okay, but don't forget the warning. Use it only for small changes in temperature and use it only for metals. Okay, don't try to use it for anything else ever. All right, so that's it, right? Okay, so now I think we should solve a question or two regarding this. Okay, I think there is an exercise question. There is an exercise question, if I'm not wrong. Okay, so that exercise question is 4. I'm going to the exercise. You also please open that page out. Okay, that question is number 5. Question number 5. Right? It is question 5 from the exercise. Okay. So here we have it. Right. So it is given that at room temperature, that is 27 degrees Celsius, the resistance of a heating element means resistance or some wire, right? Okay, some kind of wire. So resistance of a wire is 100 ohm at what temperature? At 27 degrees Celsius. That's given. Okay. Now, what is the temperature of the element, means of the same thing, if the resistance is found to be 117? So, in a new case, resistance is 117 ohm, and we have to find what's going to be the temperature for that, right? And we are given the temperature coefficient, matlab alpha. Okay, I hope you remember there was something like coefficient of linear expansion. Just like that, this is coefficient of resistance. All right, temperature coefficient of, this is the temperature coefficient of resistance. Okay, yeah. So alpha is given, right? Alpha is given to us. It's here. Now, how to solve this question? See, fairly simple. We are going to take we are going to take this one 27 degrees Celsius, right? Okay, and we are going to use it to find the other one, right? Okay, we are going to use it to find the other one, but see, here you have to be careful, everyone. Here you have to be careful, right? When we write this formula, R is equal to R0 1 plus alpha delta T, right? Okay, then instead of delta T, you can of course also write T minus T0, right? T minus T0. So that is change in temperature. You should understand that R0 is the reference resistance and T0 is the reference temperature. All right. So of course this is at T equal to T0, right? This is at T equal to T0, right? Now see, this can be very confusing. Let me tell you, તમે બહુ ધ્યાન રાખશો ને તો આમાં confusion થશે, right? Okay, here nothing is given about reference temperature. We don't know what is the reference temperature, but I've seen that in this book, listen to this carefully, in this book, unless specified otherwise, we take this reference temperature to be 0 degrees Celsius. Is that clear? આ ગોખવું પડશે અને કોક વાર આવું નહીં કરે, તમારાથી જે થતું એ કરો. right? If you want to complain, you can go and complain to CBSE or NCRT or Gujarat board. I don't care, right? There's nothing I can do about it, right? Often we take reference temperature as this, but like I said, often, not always, right? I have seen some questions where we don't take it, right? કઈ લખેલું ન હોય એ કેવી રીતે ખબર પડે એ મને આજ સુધી ખબર નથી પડી. તમને ખબર પડે તો મને શીખવાડી દેજો. Okay, so let's start. So I'm going to call this R1 and T1. I'm going to call this R2 and T2. I hope that makes sense. Clear? So let's start. So here we don't know what is the reference resistance. Is this clear? I'm going after case 1. So what's the use of case 1? So that we can find what is T1. Sorry, so that we can find out what is R0, excuse me. Right, I'm going after case 1 so that we can find out what is R0. Okay, so let's start. R1, do we have value of R1? Yes, 100 is equal to R0, 1 plus. What's the value of alpha? Write that. Use your calculators, everyone. Let's do it fast. Okay, into T1. T1 is 27 minus reference temperature. We are taking 0 degree Celsius. Kelvin ma convert કરવાની જરૂર નથી. I hope you remember that temperature difference is same whether you do it in Kelvin or in degree Celsius. Right? So finally, you get 100 is equal to R0 over here 1 plus 27 into 1.7 into 10 raised to minus 4. Leave it like that. Okay, nobody cares. Leave it like that. Clear? So finally, R0 is 100 divided by 1 plus 27 into 1.7 into 10 raised to minus 4. All right? So this is R0. Now this R0 we will use in case 2, and so that we can find out temperature. Okay? This R0 we will use in case 2. So case 2's equation. R2 is equal to R0 1 plus alpha T2 minus T0. Okay. Now, we know what's the value of R2, don't we? What is the value of R2? 117 equal to 100 upon 1 plus 27 into 1.7 10 raised to minus 4 bracket 1 plus alpha 1.7 10 raised to minus 4 into T2 minus 0. Clear? Okay. Now, so now you can start doing the calculation here, right? Do the calculations now. So first of all, I want you to find this and see, do not round it off. Please, everybody, do not round anything off. If you round it off, you will get wrong answer. Do it exact. I think I will do it, right? That will make it fast. So 1.7 into 27, right? Divided by 2, 3, 4. Okay. Plus 1. Okay. Divided by 100. And its reciprocal. So 70. What's that answer, Rupa? So we are getting 99.543, and here 1 plus 1.7 into 10 raised to minus 42, right? So finally, if I'll divide, I'll get 1.7 into 10 raised to minus 42 is equal to. Looks like people have got answers. Okay. Right, Kea? I'm getting 1.17537. Is this what all of you get? Okay, Darshi, you've got the answer as well. All right, Dhyan. So this is what I've obtained. So finally, T2 is going to be division of these two. Oh, sorry. Yeah, so that is 1.17537 divided by 1.7. I'm getting a wrong answer. So when we will subtract this one, we will get this, right? Okay. Yes, I didn't subtract. Agreed, agreed. Yeah, I just noticed that. It's a bit overwhelming, right? To calculate and to write and, you know, so 0.17537 divided by 1.7. Yeah, I'm getting 1031. I'm getting about 1031.5 degrees Celsius. But yes, because we have used so many digits, something is going to be off, right? If you perhaps make this 4 here, then you might get a slightly, bigger answer, right? I don't know what's the answer given in the book, frankly, right? But we're getting close to 1031. Okay? જો ટાઈમના પાક્કા લોકો વયા ગયા, સમય પૂરો ન કરવા દીધો. Fine. So for those who have stayed, here is the bonus, right? What if you don't want to write all this? Have a look, right? We have this relation. હા, પણ એ એકાદો ઝીરો તમે ઓછો વધુ લેશો એક ડિજિટ એટલે આવી જશે, right? So delta R is R0 alpha delta T, correct? So if you use it twice, okay, છે જ તે પણ આમાં બહુ easily લખાઈ જશે. I'm dividing, okay, we are going to divide this equation by using it twice. I hope that makes sense to you. Agreed? Clear or not clear? Okay. So if you find R0 first, right? Let's say you find R0 first over here, right? By putting the value, then you can directly jump on to this, right? And if you do this, it becomes quite simple. I hope you realize why. Because now we have R2 is 117 and you would have found R0, I think it's 99 point something, right? And this was 100 minus 99 point something. Okay. So if you do it this way, then you don't really have to worry about a lot. T2 minus T0 is 0 upon T1 is given, right? T1 was what? 27. Yeah. Clear? Okay. So if you do it like this, then you'll be able to get the answer in a little bit short, right? You don't have to write all the long things. Fine, so that's it. So this is an alternate method if you want to do it. Okay. Test will be board level only, right? Okay. It is valid, Chaitya. This formula is given in your book also at some place. All right. Okay. It is valid. Don't worry, right? This will work. Right? You will get marks also. Don't worry about it at all. Fine. So that's it. We are going to stop over here. Right? Goodbye, everyone.